Hello, Pre Calc. This is chapter 12.3, and it's called the tangent line problem. And this is probably one of the most famous entry-level calculus types of things that you can do. We do it here at the end of pre-calculus so that you're just basically ready to go for calculus, and you can start this idea of an instantaneous rate of change at a given point. And it's called the tangent line problem. And if you remember back from geometry, a tangent is something that just comes and it barely clips something else. It just clips it and then it continues on. So a tangent would be like this, where this ruler comes and it barely clips through. It doesn't go through it and pierce it. It just barely clips it. Maybe here's another tangent. It's not a tangent line, but a tangent ruler. It's almost like a rock skipping off the top of a lake, where it just comes and it glances and it barely hits it. So what we're going to do today is we're going to find ways of telling what the slope of the tangent line is at any point on a graph. And we call it the tangent line problem. So what I have here is I have a start. I have a y equals x squared graph. It looks like the vertex got moved over to 5 and up to 8. So I mean, we could come up with the equation of this line. It looks like let me undo that. Looks like the equation of this parabola would be y equals, and I went over 1, 2, 3, 4, 5. So x 5 to the right squared plus 1, 2, 3, 4, 5, 6, 7, 8 plus 8. If I was to graph that on my graphing calculator, I would get that. The question is, what is the slope at a specific point on the graph? And that's the limit. We'll use limits to do this. So here's a purple one. I have purple here. We wanted to find the slope of that purple line. I'd be right here. Well, I'd go up 1, 2, 3, 4. And it looks like over 1. So up 4 over 1. So the slope of this purple part is 4 over 1. The orange one goes straight across. The slope of a horizontal line is 0. So I got the slope here is 0. And I got this green one. Well, let me see. It goes through about right there. So down maybe 1, 2, 3 over 2. Down 3 over 2. So my slope is negative 3 over 2. And I got this black one way down here. I mean, I don't even have points. I don't know. It looks like it goes about halfway in between. So maybe up 1, 2, 3 over 1. Maybe up 1, 2, 3, 4. If I extended it up. 1, 2, 3, 4, 5, 6 over 1. Looks like it's going to go maybe 6 or 7. I don't know. We're close. We're estimating. But it is going down, so it'd be like down 6 over 1, or maybe it's down 7 over 1. And there would be algebraic ways of determining that. But that's the slope at just different points on the graph. And that's kind of hard to do, especially if we didn't have a graph. And what calculus will do, and what we'll be able to do in here, is we'll be able to find the slope at any point along the curve, regardless of where we're at. And it'll be very equationally and very exact. It won't be plotted on a graph and try to count. It'll be, can I look at it and can I tell what the slope of that line is? So that's the idea of the tangent line problem. Can you find the slope at a given point on the graph? And it turns out the slope has another idea. It's called the instantaneous rate of change at any given point. So like right here, if you were on that point and you asked yourself, how fast are you changing? Well, it consistently changes at different rates, but right there, exactly at that point, it's changing by a rate of 4 over 1 at that exact point. Okay, and that's something we haven't been able to do yet. So here's the idea. You're given the point 2, 2. I got this point right here, and it lies on that parabola. Point 2, 2 lies on the parabola. What is the slope of the tangent line at that point on the parabola? I don't know. I'm gonna try to graph in the tangent line here, I guess. Let me see if I can do that. Something like that. It skips along and it goes like that. Okay, so it barely comes in and barely clips the graph, and I just drew it in, and again, this is a very non-exact way of doing it, but it looks like it's up about 2 over 1. I didn't quite hit there, but maybe my line's a little bit off, down 2 over 1. I'm going to call this slope up 2 over 1. The instantaneous rate of change at that graph looks like up 2 over 1. Sorry, up 2 over 1. And if I change points on the graph, if I came down here, I'd have a different rate of change. It'd be straight across. It'd be constant. It'd be 0. And over here, the rate of change would be negative. But at that point, it's that. And what we want to ask ourselves is what's an algebraic way of getting there? So here's what I have. I have a series of graphs. And I want to look at these graphs, and I want to progress from A to E. And what we're talking about here is what would I get, what would be the slope of the line if I connected the yellow dot to the black dot? Well, it's down about 1 over 1, 2, 3, 4, down about 1 over, and the slope right there. But that's really not this line. That's a really bad approximation of this line. So let's try this one. Well, let's try the slope. So up 1 over 1, 2, up 1 over 3, maybe a slope of a third. But that's really not that blue line. That's really not a very good approximation of the blue line. Here I am again. I could count the slope. Not a very good approximation of the blue line. Here I am. I could look at the slope. Oh, well, that's pretty close to the blue line. And then here, I'm going to look at the slope. And wow, that line between that yellow dot and that black dot is almost the same line as the blue tangent line. Here, these 2 points were far away. And as the points got closer and closer and closer to each other, as the points approached each other, what happened was we got a better and better approximation of the slope of that tangent line. And that's really the overriding idea of the tangent line problem. What would happen if we picked 2 points on the parabola and we made one of those points go around the graph and get really, really close to the other point so that those 2 points almost lie right on top of each other, but not quite. Like there's still a little gap there, but if those were like microscopically close, like so close you couldn't even tell the difference between the 2 dots, but there still was a difference. That slope of the tangent line would be the exact same as the slope of the line between the 2 dots. And that's the overriding calculus idea here. Now, let's talk about the notationally now, okay? So the yellow dot is a point x1, y1, and the black dot is a point x2, y2. And we know how to find the slope between 2 points. The slope is equal to change in y over change in x. Delta y over delta x. We know it's also y2 minus y1 over x2 minus x1. That would be those two. Okay? But what we want, we don't want that big a gap there. We would rather shove those around, and we also want to kind of change the notation, because what we want to do is we want to shove that point around that graph. In other words, we want to decrease this value. We want to take that h value and we want to shrink it down. So I'm going to change some notational here. So this is the point x1, x1, and this has x2 there. But that distance is h. So theoretically, this point, this x value here, is x1 plus this h value. x1 plus the h value. That's what x2 really is. And y2, well, y is another term for f of x. Actually, it's f of x1. So y2 would be f of x plus h. x1 plus h. Okay? And that function notation, x plus h, f of x plus h, is another way of saying x2, y2. And what I can do is I can take that x plus h and I can plug it in for that x2. And then I can take that f of x plus h and I can plug that in for y2. So I'm going to do that. So I'm going to take this value, which is the same as y2, and I'm going to plug it in. So it becomes f of x plus h minus y1. And we already said y1, another term for y1 was minus f of x, all over x2. My x2 value is x plus h. My x2 value is x plus h, and my x1 value is still x1, so minus x1, or just minus x. I know I dropped the ones there. I could have little subscripted ones in here. And let's simplify. The top becomes f of x plus h minus my f of x, all over, well, the x's cancel out, and I'm left with all over h. And that formula is another form of that formula. But what I would really like to have happen is I would really like to have this h value shrink down to a minuscule value where I can't even tell the difference between the 2 points. I would like to make these two things go together. You know what I would really like is I would like to find the limit of this. I would like to find the limit of this as h goes to 0. If I could shove that h value distance down to next to nothing, I would have a really good approximation for the slope of the tangent line. And that's a formula that we've seen before. It is a common formula. It is a calculus formula that I'm going to show you how to use. Find the limit as h goes to 0 of f of x plus h minus f of x over h. Let's see if I named it here. It is actually called, symbolically, here's the formula. We're trying to find the limit, the slope of the secant line is equal to the limit as h goes to 0. The slope of the secant line is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Boy, this thing has a lot of names. It really does. It is a powerful formula. What it does is it gives you a formula for the instantaneous rate of change at any point along a curve, which is a big-time calculus concept. Let's go and let's see how that works within a problem. Okay. Here's example 1. Find the slope of the graph of f of x squared, of f of x equals x squared at the point -2, 4. We're going to find the slope of the tangent line here. And then we're gonna shrink that distance down next to nothing for that tangent line, and we're going to do it with that formula. So we'll find the limit as h goes to 0 of f of x plus h, and I'm going to switch colors a lot, minus, oops, hit it, minus f of x all over h. And I have it in 3 parts because this is a 3-part formula. One thing I can probably do right off the bat is I can graph it. It goes through 0, 0, 1, 1, and 2, 4, negative 1, 1, negative 2, 4. And here is the graph. And what they're asking is at -2, positive 4, right here at that point, what is the slope of this tangent line? And I can see it's negative. I could probably count it out and get close, but the idea of doing this process is to get an exact value. So here we go. Let's find the limit as, let's find this red part here. So find the limit as h goes to 0 of f of x plus h. What it tells is it tells me to take the x plus h and plug it in for the x. So it becomes x plus h quantity squared. That red goes in for that x squared. Minus my f of x value, and my f of x value is x squared, all over the h value. Okay, what we would like to be able to do now is we'd like to be able to simplify this. So what I'm going to do first is I'm going to FOIL this out. This is x plus h times x plus h. Write it up here, and I'm going to FOIL. That's x squared. xh and xh is 2xh. h times h is h squared. Minus x squared all over h. And I still do want the limit as h goes to 0. The limit as h goes to 0. And you might notice if you were to plug in zeros, you plug 0 in here, you get 0 plus 0, and x squared minus x squared is 0. The top would be 0. If I plug 0 in on the bottom would be 0. I get 0 over 0. That's the indeterminate form. We have to do something else. We have to apply a new process here. So here we go. Find the limit as h goes to 0 of this. We have it here. I notice these two cancel out. I'm left with the limit as h goes to 0 of 2xh plus h squared. I'm just going to keep it all red right now, all over h. All right, so here, I need to keep going. I'm going to find the limit as h goes to 0 of. I'm going to factor an h out of both of those. If I factor an h out of that, I'm left with 2x. If I factor an h out of that, I'm left with 1h all over h. H's will cancel. I want to find the limit as h goes to 0 of what's left over, 2x plus h. I got it into a polynomial format, which means I can use direct substitution by taking the 0 and plugging it directly in. And when I plug the 0 directly in, I get 2x. And when you go through this process, what you just found, this is an equation for the instant rate of change aka also known as the slope, instant rate of change, or the slope of the function that we were dealing with, which was f of x. So this 2x means I can go up here to this point, and what it's telling me is at that point the slope is 2x. Well, my x value is negative 2, so my slope is 2 times the x value, which is negative 2, or my slope is negative 4 at that point. So let's go here. Down 1, 2, 3, 4 over 1. I pretty much hit it. I was off a little bit, but down 4 over 1 is the instant rate of change. And I could find the instant rate of change anywhere on that graph. I could go to a point here, I could plug in the x value, and I could find the instant rate of change. All right, let's do this one. Find the limit, find the slope with the limit process. Now, before I even do it, I know the instant rate of change because this is a line. The instant rate of change is negative 2. So if it's a line, I know the answer. I'm still going to use this process because it still works, but let's go. Let's try it with this limit process. I know my answer. I know what it's going to come out at. I'm going to find the limit as h goes to 0 of f of x plus h. Tells me to take x plus h and put it in for that x. Minus f of x minus the function, which is negative 2x plus 4, all over h. That's the formula. F of x plus h minus f of x all over h. Let's simplify. I'm going to leave it all in red now. The limit as h goes to 0 of negative 2x minus 2h plus 4 plus 2x minus 4. And all over h. And I should say something right now. If you're doing this process, you're going to get things to whap out. It's part of the formula. Built within the formula, there's going to be some things where things just naturally cancel out. If you're doing it and something doesn't cancel out, you probably did something wrong. So I'm going to take, I'm going to look for it. So the 2x's go away and the 4's go away. And I'm left with the limit as h goes to 0 of negative 2h over h. The h's cancel out. And I'm left with the limit as h goes to 0 of h goes to, let's back that off. Limit as h goes to 0 of negative 2. And we've learned that the limit of a constant is the value of the constant, so I get negative 2. And what that's saying is negative 2x plus 4, here's plus 4, here's down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Here is my graph. Y equals negative 2x plus 4. What this is saying is, at any point on the graph, the instant rate of change, the slope of the graph, is negative 2. And that fits with what we know about both the graph and the equation. So this limit process actually got us the right answer. All right, let's do one more. Okay, and I'm going to go back a little bit slower here on this one again. We have this x cubed plus 1, and I'm going to graph that guy. Let's graph it in blue here. Johnny Travolta plus 1, so it's up here, and it looks like that about Johnny T. And the slope at any point, if you went wherever you're going, I mean the slope, it's going to change depending on where you're at. And it actually kind of really flattens out there at 1. can't see that, but let's go ahead and find the limit. So I'm going to rewrite the formula, the limit, as h goes to 0. Let's go back to our color coordination that we've been using. The limit as h goes to 0 of f of x plus h minus f of x all over h. That's the formula. That formula is standard. It will always be the same. Okay? Let's go ahead and find these values. Okay, so x plus h, this red part tells me, take the red part, x plus h, and plug it in for the x. The limit as h goes to 0 of x plus h in for the x. X plus h cubed plus 1. X plus h in for that, I still have a cube and I still have a plus 1, I still have my cube and I still have a plus 1. Minus f of x, minus my f of x, I use all of that, x cubed plus 1, all over the h value, all over the h value. So there it is, set up in formula, set up in the formula. That's just the formula. I haven't done any algebra. I applied this formula to that picture. Okay? Now, the hard part about this one, and the hard part when you get this number gets cubed or the fourth or whatever, is you're going to have to take this part out and you're going to have to FOIL it out. So I'm just going to go over here, a little sidebar thing. I'm going to go down here. I'm going to take x plus h and I'm going to cube it. I'm going to go down here. X plus h times x plus h times x plus h. I'm going to have to FOIL all that out in order to get an answer. So let's see what I get. X squared, and that's xh and xh is 2xh, and that makes h squared. And then I have to multiply that by x plus h again. So I'm going to multiply those two, which gets me x cubed, those two, which gets me x squared h, those two, which gets me 2x squared h, those two, which gives me 2xh squared, those two, which gives me xh squared, and those two, which gives me h cubed. And you can see why it's kind of a tedious process, but we'll still get there. We got x cubed. Let's see how many x squared h's I have. Well, I got 1 here and I got 2 there. So that's 3x squared h. And I got these two. I got 1 there. I got xh squared. I got another xh squared. So there's 1 and 2. So I got another 3xh squared. And then I have h cubed. And that is the value that I need to plug in up there where I had that thing. So let's go back up here. I'm going to draw a line here. Let's try to. All right. So what I got is I got the limit as h goes to 0 of, that's x cubed plus 2x squared h plus 3x squared h plus 3xh squared plus h cubed. That, just that little chunk FOILed into that. I still got plus 1. And I forgot my parentheses, so I'm going to be smart. I'm going to go back here and I'm going to add them in. It was minus all of f of x. So I have to subtract the whole part of f of x. I almost made a mistake. That is very common. So I go minus x cubed minus 1. And that's all over h. And like I mentioned earlier in the video, if you're not getting things to wipe out, you're probably not doing something right. So let's look for everything that wipes out. The x cubes are gone. The 1s are gone. So what's gone? So here we go. I'm going to write it all in black. Find the limit as h goes to 0 of 3x squared h plus 3xh squared plus h cubed all over h. And I'm going to look at this and I'm going to look to factor something out. They all have an h in there. Find the limit as h goes to 0 of, let's pull an h out of that one. I'm left with 3x squared. Let's pull an h out of that one. I'm left with 3xh. Let's pull an h out of that one plus h squared all over h. And those h's will wipe each other out. That's the whole reason we get to that point and we factor it. Okay. That was all the algebra to now to be able to find the limit as h goes to 0. So now as I shut the h value to 0, I'm going to plug 0 in here, and I'm going to plug 0 in here, and I notice I get 3x squared plus 3x times 0 plus 0 squared. I get 3x squared, which is the slope. Let's put slope at any point equation, or their instantaneous rate of change at any point equation. It's actually called the derivative, which is kind of cool. It's so important, so famous, it has a name, but we just haven't gotten there yet. So I got this equation. Okay, I did all of that. That was a lot of work. A lot of work. Some of these get kind of cumbersome. There won't be a ton of these for homework, not when it's that kind of stuff. And we'll do some of these together in class also. But what we want to do is we want to go back up in here and we want to apply it. So I got 3x squared. So it wants me to find the slope at the points negative 1, 0. So here I am at negative 1, 0. What would be the slope at negative 1, 0? M at negative 1, comma 0 says take the x value and plug it into that derivative. Take 3x squared and take that negative 1 and plug it in for the x. So I take 3 times negative 1 squared. Well, that's 1 times 3 is 3. So it should be up 3 and over 1. 1, 2, 3 over 1. 1, 2, 3 and over 1. My graph's a little bit off, but looks like that. The 2, 9, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's all the way up here. That graph goes through. What's the slope at that point? Well, it's pretty steep. So the slope at 2, 9 says take the 2 value and plug it into 3x squared. So 3 times 2 squared. 3 times 4 is 12. The slope way up there is 12. So up 12 over 1 or down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 over 1. Something like that. That's a pretty good idea of the slope. And that slope, again, that's the instantaneous rate of change. Instantaneous rate of change on graphs that curve and do all that, that's a huge concept in classes like statistics, economics. Heck, World Health Organization looks at curves and looks at how fast things are changing. Population growth is changing. Different types of disease, how fast they're growing. Instant rate of change is a really big concept for upper level math. So you got a little bit of background in it. We'll do some more with this, and that's it.